In the last video, I covered the overview and my goals for the project and some key design selection. I touched on the subject of the box, robust and lightweight, standardized size, options for multiple suppliers. In this video, I will cover the part of moving the box on and off the cart. The principle of moving the box on and off the cart was easy, but I had to move the box further out than the cart was long and therefore extend more than physically possible with my initial idea. More than twice the length, as the arm has to extend longer than the cart plus the gap between the cart and the shelf, and reach behind the box on the shelf to grab it and pull it onto the cart. My first thought was to make a compact and slim solution with tube-in-tube, but before long I came to the issue about how to make the tubes go further out than one pipe was long. Okay, next plan, 3 tubes in tubes. I considered using a pneumatic cylinder to do the moving, but they have a limited range, so I had to have 2. One pushing the other to get the required range, plus all the hoses and the valves for air and controlling. Making the mechanics inside the square tube was way too complicated for my box of available tools. So a new strategy had to be found. Online, I found examples on how cranes were built. I started my own 3D printed version using the smallest square tube I had. The experiment ended out with this model. The mechanics and theory on how to extend the pipe beyond the edge of the cart was solved. A little simple and without any finesse, but it did the job. I had not added bearings of any kind, so the friction when the arm extended more than 50% got too big to be of any use. One solution was to add yet another set of pipes, but the size of this demo was already way too big and clunky. I spent a lot of time in my CAD software trying to add bearings to lessen the friction, but ended up with a structure that was even bigger than adding an extra set of square pipes. The experiment let me acknowledge that building the arm myself was way too time-consuming, and the result would be too complex and difficult to use. I learned how not to do it, and started searching for overextension telescopic rails online. I found what I needed and ordered 2 pieces. They were very sturdy, smaller than my own design, and could extend well beyond my needs, like 200%. Next issue popped up: how to move the outermost arm further out than the end of the main arm mounted on the cart. Some 3D printing, thread cutting, and a number of small modifications later, I was able to move the arm all the way. Now I had my sliding arms that could reach farther than needed without the friction consuming all power. I found a motor that could move both arms at the same time, made the mounting brackets, found the right axle mounted flanges, designed and printed the spools for the wire. Getting the wire routed from their termination points on the sliding arm to the spools was a challenge, using a number of bearing pulleys for wire and odd angles. In my CAD software made some strange looking 3D printed elements that solved that problem. Now I can use the motor to move the arms in and out. An issue not covered yet is how to detect the arms are in their inner and outermost position and then stop the motor before it tears everything apart. The inner stop is for now planned to be a micro switch mounted on the bar. As of now, I have planned to use a rotary encoder mounted on the motor to count revolutions. To make this work, I have to figure out how to make the code for my ST microcontroller board. The code must be able to count the number of revolutions and stop the motor when it reaches the correct position. I have considered adding a motor controller to manage the speed of the motor. This controller will let the motor start out slow and gradually build up speed until it gets close to the end, and then wind down the speed just before it reaches the end. This speed up and down will lessen the physical load on the mechanical structure and make the movement of the box more smooth. Furthermore, when the system has to recover from an unknown state, the option to retract the arms slowly will reduce the risk of damage to the mechanical elements and their surroundings. One more thing to tick it off on the list. The switch and rotary program will come eventually. Next video on this project will cover the arm to restrain the box at the end of the extending arm. I'll show the 3D print designs and a short show and tell about the learnings I had during the development of that small part of the project. Until next time, enjoy.